Hello and welcome back. In the previous video, we had just done a couple of examples where we were trying to find the angles between vectors using our formula. And the way this works is we take the dot product and the absolute value of that. This should be equal to the length of u times the length of v times the cosine of the angle between them. And so it's just finding a dot product, finding the lengths of a couple of vectors, and using our cosine to find that angle. In this case, we had I and j, but we know that if I draw a picture, I is pointing straight to the right because it's pointing in the x direction. J is pointing straight up in the y direction, so the angle between them should be 90 degrees. And we found that that was the case. Their dot product is 0, both of their lengths are 1, and when we take the cosine of what angle is going to be 0, well, between 0 and 180 degrees, the only one where the cosine is 0 is at 90 degrees. So let's think about this guy for a second. We've got two vectors that are pointing in the same direction. So what's the angle between a vector and a vector pointing in the same direction? Well, that angle should be 0, right? There is no separation between them. Let's check and make sure. So we need to take the dot product of these two guys. And this is going to be 1 times 1 plus 1 times 1 plus 1 times 1. So that's going to be 3. And then I need to find the length of both of these vectors. So this is going to be the square root of 1 squared plus 1 squared plus 1 squared, and that's the square root of 3. So plugging everything into my formula, I have the absolute value of the dot product, so the absolute value is 3, is equal to the length of one vector times the length of the other vector, which they're the same vector, so they have the same length, times the cosine. And then here, we know that the square root of 3 times itself is just 3. So this is 3 is equal to 3 cosine theta. Divide both sides by 3. Cosine is equal to 1. Well, where is the cosine equal to 1? Oops. It's right at 0 degrees. So we get the same thing both ways. The inverse cosine of 1 is going to be 0 degrees. The cosine starts at 1, right at 0. So everything sort of is making sense with this. We checked some that we know are going to be at right angles and some that we know are going to be at 0. So just to reiterate though, the dot product of two vectors is a number and not a vector. So this is something I really want to drill into your head. The dot product, when you take the product of two vectors, you're going to get a number and not a vector. Now, we have seen a couple of cases where the dot product of two vectors is 0. And the case in which these happen, they're going to be at right angles to one another. And we have a special term for this. This is called being orthogonal. Ortho means correct, and right is also correct. So at a right angle, they're going to be orthogonal. So we can ask whether or not certain vectors are going to be orthogonal. And all we have to do is take their dot product and see if it's 0. So we've got these two vectors, 1, 1, and 2, 2. Let's take their dot product. Oops. 1, 1 dot 2, 2. It's going to be 1 times 2 plus 1 times 2. Well, that's 4. So no, they're not orthogonal. And we can kind of see this because the vector 1, 1 is going to be pointing up there, and vector 2, 2 is going to be pointing pretty much in the same direction, just a little bit longer. So they're not orthogonal. Let's check these guys. 1, 0, 3 and negative 6, 2, 2. So we're going to take their dot product. 1, 0, 3 dot negative 6, 2, 2. So we have 1 times negative 6 plus 0 times 2 plus 3 times 2. This is going to be negative 6 plus 0 plus 6. Oh hey, these guys are orthogonal. This one is a little bit harder to draw pictures, harder to draw pictures in 3 dimensions, but we can check to see that they're at right angles with one another because their dot product is 0. And then let's do this final one here. Oops. So to take this dot product, we're going to take the x coordinates of these guys times the x coordinates of these guys, and the y coordinates times the y coordinates, and add them all up. So the x coordinates in both of these are going to be 1, so we get 1 times 1. And then the y coordinates, this is 1, but this is negative 1. So 1 times 1 is 1. 1 times negative 1 is negative 1. And 1 minus 1 is 0. So these guys are orthogonal as well. So it's pretty easy to check if things are at right angles to one another just by taking a dot product. The very last thing that we'll do is we will do some cross products. And the first thing I want to mention is that the cross product of two vectors, again, we write this with a little cross in the middle, a little x, and the cross product of two vectors is another vector. And as you look at this formula, this is a gigantic formula. It's got 3 parts to it. How on earth are you going to remember this? Well, you can write it down in your notes and use your notes. The other thing that I want to point out is that there is a pattern to this. So xyz cross abc, yc minus zb is the first coordinate, za minus xc is the second coordinate, and xb minus ya is the third coordinate. Where does this come from? Well, what I'll do is I'm going to write this in a big grid. So here we have I, j, and k representing the x direction, the y direction, and the z direction. And I've got our two vectors. We've got the first vector as the second row, and then the second vector is the third row. And what I'm going to do is I'm going to draw some lines through this. So I can draw a line, some diagonal lines. And I'm going to do all the ones that are starting from the upper left and going down to the bottom right. And for this one, what I'm going to do is going to go, and it's going to continue on the other side. And then for this last one, again, we're going to come over here, we're going to hit, and then we're going to continue down this other side. These are the lines I'm going to make. And I want to do this again, but what I'm going to do is I'm going to multiply all the numbers that I'm hitting. I, y, and z. So, oops, that should be a C. So this is going to be y times c times I. And then we'll do the next one. J times z, skipping back over, times a. So z, a, j. And we're going to add all of these guys up. And then the last one, we're going to start over at k, but we don't hit a number over here, so we start over from the left-hand side, and we hit x and b. So this is going to be x times b times k. Okay, we're not quite done yet, because there's a few more diagonal lines to consider, which are those going in reverse. So again, let's start from I, and there's nothing here, so we start over from the other side and go zb. So we have z times b times I. And since we're going backwards, since we're going from right to left, we're going to subtract this one. Hopefully, by the end of this, you'll see that these match up. Okay, so then we can start from j and start going backwards. J, x, c. And again, because we're going backwards, we're going to subtract this. And then we've got one more to do. So we've got going backwards from k, This is the nice straight one. So we're going to have y, a. And what you'll see is that if I add all these up, well, I've got some like terms. Let's do some blue. I've got some like terms here. So that's y times c minus z times b, and all of that is taken times I. Oh, and look, yc minus zb, those match. Let's do another pair of like terms. We've got a couple of j vectors. We have za minus xc, and all of that is being taken times j. And that matches. And then the very last one is going to be xb times, or xb and a ya. And that's how we take a cross product. So let's do an example, because I think this is quite a lot to take in. So let's just do an example. I'm going to write down my little 3x3 grid, and I've got 1, 2, 3, and 4, 5, 6. And let's go through my diagonals. So the first diagonal, pointing down and to the right, is going to be I. It's going to be 2 times 6, which is 12. The next one, we're going to have the vector j. We're going to hit 3, and as we wrap around, we're going to get 4 on the other side. So 3 times 4 is also 12. And then the last one, k, we're going to start coming down. We're going to hit the k, and we're going to wrap around to the 1 and the 5. So and 1 times 5 is 5. So far, so good. Now, let's go in reverse. We're going to work from right to left. First up, I. We hit I, we wrap around, and we get 15. We get 3 times 5. So that's 15. And since we're going backwards, we're going to subtract this. Next, starting from the j, going backwards. J times 1 times 6. So 1 times 6 is 6. And again, we're going backwards. We're going to subtract this. And then the very last one, we're going to start with k. We're going to hit 2, and we're going to hit 4. So 2 times 4 is 8. And again, we're going backwards, so we're going to subtract this. 12 minus 15 is negative 3. 12 minus 6 is 6. 5 minus 8 is negative 3. Here is my cross product. Negative 3i plus 6j minus 3k. And that I can write in this notation as negative 3, 6, negative 3. So, there's your answer. Let's do one more example, and let's make it a silly example. Silly examples are nice. Let's take something cross itself. So we've got I, j, k. 1, 2, 3, 1, 2, 3. Let's do our diagonals. Going to the right, we have I times 2 times 3. So 2 times 3 is 6. Next up, j times 3 wrap around times 1. So 3 times 1 is 3j. K times 1 times 2. 2k. Going in the other direction, let's subtract these now. I times 2 times 3. 2 times 3 is 6. And we're subtracting. J times 1 times 3 is 3. And then the last one, k. K times 2 times 1. 6 minus 6 is 0. 3 minus 3 is 0. 2 minus 2 is 0. we get the 0 vector.